For problem 4.28, we need to find R for an output voltage of 50 millivolts. So we need to find R for an output voltage of 50 millivolts. Considering that the diodes that we have in the circuit here, they are equals. So basically it means that for us that the saturation current 1 is equals to the saturation current 2. They're the same diode. Okay, now if you look at the circuit, we have a voltage, a current source here that forces 10 milliamps to flow inside this node here. Part of this 10 milliamps they flow across this D2, and part of the other part of the 10 milliamps flow here over this branch with D1 and R. Okay, now if we look at this circuit, basically the current, if we have current flowing in this direction here and this direction here, they are basically allowed for the diodes to conduct in that direction. And one thing is that the current that's flowing here through this R is the same current that's flowing through this diode 1 because they are in series, right? So one thing is that we can write that the current ID1 is equals to the current flowing through this resistor, which in our case is V0, right, minus 0 divided by R. So it's V0 divided by R. That's our first equation for current flowing through diode 1. Now, because we know, so if we know this current here, right, this current here is ID1, this one here is ID2, right, we can write ID2, so let me write ID2 as those 10 milliamps that are reaching this node here, right, this 10 milliamps from the current source, minus ID1, so minus V0 over R. Okay, that's the equations that we have for ID1 and ID2 from this first analysis of the circuit. Okay, now let me just simplify a little bit this drawing here. Okay, now if we look at the diodes, diode D2, it has VD2 here, diode 1 has VD1 here, right? That's the voltage across each one of the diodes. If we apply a loop analysis here, we have minus VD2 plus VD1 plus V0 equals to 0, which basically gives us that V0 is equals to VD2 minus VD1. So this is a third equation that we have from the circuit. First one is this one here. Actually, this is the first one, this is the second, and the third one. So we have those three equations, right? So current ID1 flowing here, flowing here is the same as the current flowing through the resistor. So we just take the voltage V0 across the resistor and divide by the resistance, equation 1. Then here we just apply a nodal analysis. So the sum of the currents entering the node should be equals to the currents that are flowing outside the node. So this one is entering minus this one that it's leaving gives us the net current leaving here this branch through D2, so ID2, and then a loop analysis that the sum of the voltages in a closed loop should equals to 0, okay, KVL. So we have those three equations. Now we also know that for a diode, ID is equals to the saturation current exponential of VD, so the voltage across the diode, divided by the thermal voltage, right? And for the specific case of those two diodes, this IS is the same because the problem says that diode 1 is equals to diode 2, so they have like the same characteristic, the same manufacturing, so they present the same saturation current, okay? And in this case, ID1 is equals to IS exponential of VD1 divided by VT, and ID2 is equals to IS exponential of VD2 over VT. Now one thing here is that we can use the property of the exponential function to basically obtain this ratio here VD2, so this equation VD2 minus VD1, which is V out, by taking the ratio of ID2 over ID1. That's IS exponential of VD2 divided by VT divided the entire thing divided by exponential of VD1 divided by VT. Now those two here, they cancel, but these functions here, because we have an exponential dividing another exponential, is the same as exponential VD1 times VT divided by VT times exponential of minus VD1 divided by VT. Okay, so let me write that so it's clear for you. So ID2 over ID1 is the same as exponential of VD2 divided by VT times, now because this one here is the denominator, we can take as the minus VD1 VT, which is the same because we have the same base here, the exponential is the same base. We can add now those exponents, and this gives us the ratio that we want. So ID2 over ID1 should be equals to exponential of VD2 minus VD1 divided by VT. Okay, so that's the ratio that we have, and this is equals to exponential of V0 divided by VT. Because of this loop analysis here, we know that VD2 minus VD1 is equals to V0. Okay, and remember the first two equations that we got from the circuit analysis? We got an equation for ID1 and for ID2, those two equations here. So if we take those ratios, we basically have an equation that depends on R, the 10 milliamps that we know, and V0. Okay, so let's write that equation. So we know that ID2 is equals to 10 milliamperes minus V0 over R, and that's divided by ID1 that we know that is V0 over R. That should be equals to exponential of V0 over VT. So if we multiply this one by V0 divided by V0, which is the same as multiplying by 1, we get, or divide both sides by V0. Okay, so we get 10 milliamps, or not V0, multiply by R, right? R divided by R. So we get rid of this R here and there. So it's 10 milliamps times R minus V0 divided by V0 should be equals to exponential of V0 divided by VT. And now we can isolate R in this equation. So we get 10 milliamps R minus V0 is equals to V0 exponential of V0 over Vt, and then R is equals to V0 plus V0 exponential of V0 Vt divided by 10 milliamps. And we know V0, we want V0 equals to 50 millivolts, millivolts. So if we substitute this in this equation here, we get 50 millivolts plus 50 millivolts times exponential of 50 millivolts divided by the thermal voltage. So because the problem doesn't say anything about the thermal voltage, we always consider it as 25 millivolts. So we just divide by 25 millivolts and everything here divided by 10 milliamps. Okay, and this gives us a resistance of 41.94 ohms, which is approximately 42 ohms. And that's the answer.